Okay, welcome to this talk, and thank you, Steve, for your nice introduction. Since this is the last talk before the coffee break, I'll try to make this quick and painless. And second slide, this is the one, and you can see why Steve thinks this is a very interesting slide. Had I realized, of course, that he would be on the front bench to check my quotes, I would have triple-checked what I was quoting accurately. So I hope I'll pass. But this talk was, in a sense, inspired by Steve's presentation to NANOG in Miami a couple of months ago, where he talked about his vast experience in internet exchanges over the years. And he gave us a list of myths that he had come across, and that turned out to be, well, myths. So, as I quoted here, myth number one on this list, I like that one a lot, which 10 megabits is enough. And of course, with today's hindsight, that's something we can smile upon with some tenderness, at least. Things have changed a bit, but back in those days, things were different. Now, as Steve said back then, this worked great until it got full, and this is basically where I got triggered, because that it got full, that's what we have a lot at M6 as well, so I could relate to that. And so what I wanted to try here today is give you some examples. So we are dealing with the it gets full in our domain, and what we've done in terms of upgrading, and particularly how we think that we've done a good job easing our own lives with implementing optical switching in our network. And so that's what we'll be focusing on here. What you have here is a typical diagram of, in our case, this is accumulated customer traffic over our public facilities over a number of years. And, well, what you see there is, of course, a healthy growth figure. Well, maybe a bit too healthy, but definitely, for the most of you, this is not coming as any surprise. You're probably looking at this saying, oh, well, exponential growth, that's what we're having, what we're seeing every week ourselves. But what this definitely means for us is that it keeps us pretty busy in terms of keeping the network in shape, upgrading, expanding, etc. For instance, over the last couple of months, over the last year basically, we have upgraded all of our edge, our customer connecting equipment from Foundry Iron Core platforms into next generation Foundry Jet Core. For instance, to be able to offer trunks gigabit Ethernet connections to our customers. And but that's not entirely the focus of this talk. The focus of this talk is another aspect of the migration and the changes that we've gone through, and that is that we've changed our infrastructure from a ring into a spoke hub topology. And traditionally, or at least for the last couple of years, our network, our infrastructure looked like four interconnected locations, 4 Foundry switches connecting our gigabit Ethernet and fast Ethernet customers, interconnected by 10 gig links. And one of the issues we had with that ring structure was that we were seeing that the internode volumes, the internode traffic, was exceeding and growing and becoming an issue. And particularly because, of course, we needed to scale the entire platform and all the links involved to be able to cover the backup load in case of link failure scenarios. And we were hoping, we were expecting, we were counting on the fact that by transforming our network into a spoke hub topology, we would at least reduce the amount of internode traffic. Second argument to consider going over to a spoke hub topology was the fact that we were getting basically, this relates back to discussions internally we had during the summer of 2003. And at that point in time, we were getting the first customer demand or inquiries about providing 10 gigabit Ethernet customer connections. And we couldn't back then, and we were thinking about how we would be able to provide those. And providing them from a central core node in our network compared to providing from all of the edge nodes looked as a preferred scenario to us. Firstly, because of the fact that it would help us to again decrease the amount of internode traffic, or at least decrease the growth of that. And secondly, of course, by providing 10 gigabit Ethernet to customers from a central location, that would reduce the amount of initial hardware cost involved to provide 10 gigabit Ethernet. A third argument that worked for us, or that we felt was relevant, was the fact that in general we thought that expansion could be handled more easily in a platform in a spoke hub environment, in terms of adding additional nodes, adding additional core size. But of course, with these having at a certain point decided to migrate into a spoke hub environment, we definitely had a major concern, or well, we had several concerns, but at least one of our concerns was how to go about implementing this and not create a massive roadblock on the platform for a significant, or even for a smaller period of time. So this is where the optical switches, the photonic switches, came into our thinking, and that's what I want to go into now with this presentation. Firstly, what is optical switching in the way we applied it? Well, or what's it not actually? What we have not implemented is what I would call packet switching in the all-optical domain, and that's maybe something that people initially think of when they hear about optical switching. It's not what you read about in the press in terms of lambda switching. What you need to think about in our case is really pragmatically looking at it. We're using the optical switches as really fast, remotely controlled, automated patch panels, which provide us with an enormous amount of flexibility in the network. Now, the boxes we choose to implement are a glimmer glass fiber connection service, and these are built up around micro-electromechanical systems, so-called MEMS, a term that you might have seen somewhere or heard of. What these basically are miniaturized micro-scale moving components that are being built up with IC integrated circuit manufacturing technology, which makes them pretty cost-effective to manufacture. This diagram tries to go into that with a little bit more. What you see here, basically at the bottom, a static substrate layer onto which a micro mirror device is being built. So the mirror layer can be tilted by applying a voltage over the device. And the next slide is giving you a conceptual view of how this works. In the diagram, you see on the left-hand side a bundle of input and output fibers that are focused onto the mirror array at the bottom of the slide. And each individual mirror in that array at the bottom is individually adjustable. So a combination of two mirrors can actually connect an input fiber to an output fiber via the static mirror on the right-hand side. This photograph is giving you, this is a photograph of the actually mounted device inside the glimmer glass box, and illustrates the same concept. And the photograph on the left-hand side is an example of the micro mirror array. I think it's a 64 port array that you see there, on the same scale with what I think is a dime, so it gives you an indication of the whole size of the thing. Each individual mirror has a diameter of about 1 millimeter. Okay, so these are really nice boxes, flexible, configurable, not too expensive, but of course there has to be some bad news too. And well, it's obvious, but with all of the interconnecting to do and the mirroring in the box, there is some signal loss involved. I think it's a modest amount of signal loss. This might make it more readable. 2 dBs. Which is, well, it's not a whole lot, but of course it can be an essential amount of signal loss in some boundary cases. And then we've had some reliability issues with the initial revisions of the boxes we implemented. These things have been fixed in the meantime, and of course, since then, fortunately, the boxes have been running very smoothly. And most importantly, despite these hardware issues, we've had no service interruptions caused by these issues. So that's a good thing. Now, in the remainder of the talk, I will focus on how we've applied these photonic switches, how they're implemented in the network, and first say a few words about how we control them. And basic control of these photonic switches is taking place via a nice GUI web interface that allows you to plug and play, connect icons and buttons together. And also gives you an indication of the input and output light levels of each port. So that can be a very handy troubleshooting tool as well. But of course, for the real diehards, there's an actual shell access as well, which provides you with a command interface that allows you to enter TL1 commands. TL1, which stands for Transaction Language Number 1. I don't know how many of you have been exposed to that. I, for one, wasn't, and TL1 is a configuration language from the telco world. And my personal opinion is that TL1 actually makes COBOL programming on an IBM 360 mainframe a really nice exercise. So, but of course, then I'm not a COBOL programmer. And for lack of COBOL programmers at the M6 environment, we decided to spend a few resources on actually implementing some remote control tools to take us a few abstraction levels away from the TL1 stuff. Particularly at the bottom you will see there the photonic switch control daemon, as we have dubbed it, which is a piece of software that we've written. We run on an external box that monitors state changes in our environment, and based on the state changes, reconfigures part of the photonic switches. We'll come to that later because it's in one of my example use cases, and we're coming to those use cases right here. I have 3 use cases for you lined up. 2 of them are to do with the migration phases that we went through, and the third one is with 10 gigabit port resilience. And it relates to this photonic switch control daemon that I mentioned. Because with the idea that we would provide 10 gigabit Ethernet connectivity to our customers from a central node, we lose the opportunity of providing that resiliently, and that is again where the photonic switch is coming to help us with that. This is use case number 1, the transitioning from a ring to a spoke hub environment. And what you see on the diagram is actually our platform as it's, or a schematic of our diagram, the way it looked about a year ago. We have 4 foundry switches at 4 colo sites interconnected by 10 gigabit Ethernet. The 4 switches connect our gigabit Ethernet and fast Ethernet customers. And since this is a layer 2 environment, which may or may not be entirely obvious with your backgrounds, but we are running a layer 2 environment, so the 4 links in the node are protected against loop, or we have a loop resolution there, or had at that point in time, by running a CP. So we have 1 inactive link. Now into this environment we introduced the first photonic switch and went on to add some links into the platform, rearrange some backup links and some of our active links. And of course, added the first core switch. And if you look at this diagram, we're still in ring mode, I would say, but you can see that the actual transition to a spoke hub topology is almost the proverbial push of a button. And so that's what we basically did by transitioning to by reconfiguring a set of active links, active and inactive links that were flowing through the photonic switch. We transitioned from a ring topology to a spoke hub topology, as you see it in this slide. And the actual transition was not entirely as instantaneous as this presentation, of course, is suggesting, but it was close to that, because the actual switchover of the individual links via the photonic switch is in the order of a few hundred milliseconds. And of course, running STP or rapid STP, as it was the case in our situation, the transition took a bit of time because of the restabilization of STP. So all in all, this switchover took probably a few seconds, or not probably, certainly it took a few seconds. Now, in my next example, that's an example from a bit later on in the migration phases. And I need to rearrange the slide a bit to make some room for additional network elements. So we're still looking at the same topology, although I've rearranged all the boxes. At the bottom now you see our edge nodes. At the top there's the core node, and the photonic switch is in between. And onto this network, we added some additional, an additional core switch and an additional photonic switch to, of course, bring back the resilience that we needed. Now, what you see here is our dual star topology, which has one core system that is the active, the master core switch, and then there's a backup core switch that is keeping tracks of its master. And in case that it notices that the master is gone, or the master decides to reduce its priority because it sees one of its links fail, the box labeled core 2 in this example will take over, and the whole environment will transition to the backup configuration, enabling the links that are grayed out in this slide. Now, unfortunately, at this stage in the migration, what we had there was two core boxes that were actually temporary boxes, because what the intention was that we would provide, we would set up our core network, our core network elements with Foundry Mucha Grande devices, which were at the time that we needed to start implementing this, which were not available yet. At least in our view, they were not ready for prime time. So what we did was we implemented temporary core systems with Foundry big iron switches. And of course, or maybe not of course, but what I want to show here is that at a certain point in time, when we were convinced that the network was quite stable and things were hunky-dory, we started to look for trouble again, of course, by bringing in additional equipment, which was the new Mucha Grande device, labeled MG8-1 here. So again, the photonic switch gave us the option of easily switch over between what was their core 2 to MG8-1. And of course, with that switchover taking place in the backup environment, the photonic switch was not as essential there as it was in the previous example. However, the real value of having a photonic switch in here was actually in the fact that we could easily transition back to the situation with a core and a core 2 box, so transition to the big irons and move away from the MG8s in case that it had turned out that the MG8 was not functioning in our live environment as it was expected. Now, this didn't happen, but the core functionality of the photonic switch there was to provide us with that value, with the capability of returning back. Now, the third example I have for you is actually coming pretty close to, if you look at this diagram, it's coming pretty close to our network as it is built up today. What you see here is again the double star topology. You see one active core node and you see one backup core node. And they keep tabs on each other's health by exchanging key polars, as I think I mentioned. The key polars are exchanged with virtual switch redundancy protocol, which is a Foundry proprietary protocol. And of course, with this environment, again, as I mentioned with the previous example, in case of any network failures or in case of the fact that one of the core switches has a problem, the master core switch has a problem, we transition to the other core switch, which of course works fine for all the boxes at the bottom because they're all double connected to both core switches. But the model sort of breaks when we start to add customer routers to either of the core nodes. And that's the third example, where we provide 10 gigabit Ethernet connectivity to our customers by connecting them to either of the core switches, because we have the required 10 gigabit Ethernet port density on those switches. So we add a customer router, and the way we implement that resiliently is by hooking up via the photonic switch number 1 in this example. And photonic switch number 1 actually takes care of the connectivity from the customer router onto the active core switch. Now, in the case of a VSOP state change, that's the moment when the photonic switch control daemon that I mentioned earlier in one of my slides actually kicks in, which is the software running on our external control system. And this software is being triggered by the VSOP state changes and automatically instructs, in this case, PSW1 to reconfigure the connection from the customer router from MG8-2 onto MG8-1. So what you see here is the reconfigured network gone over to the backup state, where MG8-1 is now taking control via photonic switch number 2, and all of the previously inactive links have been activated. Okay. One thing to add here, this we've tested this model in our labs, and we've also worked with a number of beta customers, and this model works fine. And there's only one funny, well, not funny, but an interesting aspect that we've noticed with some of our customer routers that we've tested with, and that's that with a number of very fast customer routers, we saw that the actual switch over period took longer. And after looking at in some detail, for the moment, we think that the reason that this happens is that the really faster, the faster model routers that we have connected up there in these tests actually have detect a link failure or declare a link failure at the moment that the link is swapped to the other side, which is something like up to a few hundred milliseconds reconnection time. So the faster routers actually declare a link failure and need more time to re-establish the links, whereas other routers do not detect a link failure and just keep the link up. So with that, I'm almost done coming to this slide and asking myself, or asking you, are we done? Well, obviously, having learned from Steve's list of myths, we're not nearly done, and we don't expect to be done in the near future. As quoting again from the list, myth number 6 from Steve was 100 megabits per second is enough. Well, still not quite, I would say. And but the real lesson there, of course, was that you should not think that by implementing this new fancy enabling technology, you've saved your life. You've maybe bought a bit of time to prepare yourself for the next series of changes. And looking at today's traffic patterns, we're currently at something like 39 gigabits per second peak traffic on our platform. And if you look at the growth predictions based on history, we can expect something like 100 gigabits per second by the end of next year as the peak volume to take care of on the platform. And that's pretty scary. So we need to start planning today. Well, planning is a bit optimistic because we know we'll need equipment that's not on the market today. We know we'll probably need technology that's most likely not even in the vendors' labs today. So we've got quite some changes ahead of us. And but definitely we're looking ahead. And one of the things that we're reasonably sure of, based on our experience today, is that we'll have the photonic switches in the middle there to provide us with their great functions. And I hope that this presentation has given you some idea of why we think that's the case. So with that, I want to thank you. And if there are any questions, I'm happy to take them now, or considering that it's time for coffee, you're also welcome to, of course, come up to me during the coffee break. So thank you.